everyone. My name is Mihalis. Thank you for joining me for this talk. And I'll talk to you about stateless model checking. So stateless model checking is a verification technique for concurrency that verifies a concurrent program by enumerating all of its interleavings. Now, because enumerating all of the interleavings doesn't scale, stateless model checking is usually combined with dynamic partial dereduction, or DPOR for short. Now, DPOR says you don't have to enumerate all of the interleavings of a program in order to verify it. You just have to enumerate a representative subset. So for example, if these are all the interleavings of the program, DPOR partitions these into equivalence classes and then tries to explore one interleaving per equivalence class. Now, DPOR is a very neat idea. However, all existing approaches suffer from the following trade-off. They'll either explore an exponential number of redundant executions while maintaining polynomial memory consumption. And when I say redundant here, I mean that we might have a program with n equivalence classes and a DPOR algorithm exploring much more than n executions. Or we might have zero redundancy, but then have exponential memory consumption. The goal of my talk is to convince you that instead of compromising and having graphs like these here, we can have graphs like these. I'll talk to you about Trust, our truly stateless model checker that provides the best of both worlds, zero redundancy and polynomial memory consumption at all times. And more concretely, what we've done is the following. I'll present you the first exploration optimal DPOR that has linear memory requirements to the size of the program. Our algorithm is parametric both in the choice of the memory model, that is, it doesn't just work for sequential consistency, but also for weak memory models like TSO, PSO, and RC11, and also in the equivalence partitioning that it's used, how coarse or fine-grained it is. In addition, Trust is embarrassingly parallelizable. Different explorations share absolutely no state, so they can be explored completely in parallel. And finally, Trust's core algorithm has been verified in Coq. In the rest of the talk, I'm going to try and give a brief overview of existing approaches and why they suffer from this trade-off, and then show you how Trust overcomes these issues. And hopefully by the end, I'll have you convinced that Trust truly offers the best of both worlds. So let's get started. And this here is going to be my running example. We have 3 threads, and the instructions are labeled. The first thread is writing Y, the second thread is reading X, and then reading Y. And the third thread is writing 1 to X. Now, this program here has 12 interleavings that can be partitioned into 4 equivalence classes. Take my word for this. So if a DPOR algorithm is to verify this program, it has to enumerate these 4 interleavings, one from each equivalence class. So for example, in this first one here, the reads are executed after the writes. They're both going to read 1. In the second one, the reads are executed before the writes. They're both going to read 0. And then in the other two, X is going to read 1 and Y 0, and vice versa. I could have picked different interleavings. For example, I could have picked this one instead of the first one, where the writes are executed in the opposite order. But that's the whole point of this equivalence partitioning. We just have to enumerate 4. And let me show you how existing approaches do that, starting from a non-optimal DPOR. The procedure is actually pretty similar to a depth-first search. We start from an empty trace, and then the non-optimal DPOR adds events corresponding to instructions one by one. And at each step, it keeps track of the instructions that it executed in some sets called backtrack sets. This is trace number 3 from above. And once it gets this full trace here, it initiates a race detection phase. That is, it detects conflicting instructions that could be executed in the reverse order. So for example, it notices that these 2 x-axes here could be executed in the reverse order, so that the read of X could read 1. And to model that, it inserts this write of X in the backtrack set of the second transition. In a similar manner, it detects a race between the y-axes and says that I want to execute this read of Y before the write of Y, so that it reads 0 instead of 1. So it wants to add this read of Y in the backtrack set of the first transition, but it cannot do that because it's not fireable at that point. The read of Y causally depends on the read of X, so in general, it has to add some of the causal predecessors of this read of Y. In this case, there's just this read of X, and it adds that. This concludes this first exploration, and Next, it will restrict the trace to this point here, to the second transition. It will fire the right of X and then go on. But instead of showing you the rest of the exploration, in the interest of time, I'll just show you what's the difference with the optimal DPOR. The optimal DPOR obtains the same trace there, and then it starts a race detection phase. It reverses the race between the x-axes in the same manner. And then when it finds the race between the y-axes, instead of putting the read of X in the backtrack set of the first transition, it puts a sequence there, read of X followed by read of Y. Now, why does it do that? Well, the reason is that it wants to be able to reverse the race between the y-axes in a precise manner. Before, the non-optimal DPOR had to choose one of the causal predecessors of the read of Y. And this can actually be an issue. And let me show you an example. I'm not going to show you how we can reach this execution, but in some cases, even for this example here, we can reach executions like this. What I didn't tell you is that there's another set. This is called a sleep set in red. And this contains transitions that we cannot fire. And now in this state, we have fired this right of Y. So we can only fire the read of X or the right of X, but they're both in the sleep set. So this transition is going to be blocked. And actually, the non-optimal DPOR can encounter an exponential number of such blocked executions, precisely because when it reverses the race, it just puts one event there. And if there are many causal predecessors of a given event, it picks one. And if it chooses poorly, then we get such blocked executions. And this is a fundamental issue with a non-optimal algorithm. Now, the optimal algorithm puts sequences there so that it always knows how to precisely reverse a race. So it doesn't encounter any blocked executions. But now here's a funny thing. Before, the size of the backtrack sets in the non-optimal case were bounded because there were at most n different transitions that we can put there. But now, in the optimal case that we're putting sequences, these sequences can be permuted. So the size of the backtrack set is no longer bounded by some polynomial, but by some exponential number. Right? Now, here's a trade-off that existing approaches have to face. They'll either put single transitions in these backtrack sets and then have redundant executions, or they'll put transition sequences, but then have exponential memory consumption in the worst case. So trust. Trust is a optimal DPOR, the first distinguishing feature of which is that it uses execution graphs to represent executions instead of traces following GNMC. And let me show you what I mean by that. This is my running example, and I can represent the 4 equivalence classes for this program using these 4 execution graphs. In these graphs, the nodes correspond to instructions of the program, and these green edges show where the reads are reading from. So in this first execution here, the reads are reading 0. In execution number 4, both reads are reading 1, and so on. Now, why use these graphs? Well, as I said, these graphs precisely model the equivalence class for this program. So a DPOR algorithm can verify this program by enumerating exactly these 4 graphs and not by enumerating traces belonging to the corresponding equivalence class. And in addition, using execution graphs has 2 other advantages. The first one is that these graphs can represent executions under weak memory models as well, so not just sequential consistency. And the second advantage is that they also allow for reversing approximately 50% of all races in an optimal manner. And let me show you what I mean by that by running a graph-based optimal DPOR in this example. Again, we start with an empty graph, and we add events corresponding to the instructions one by one. When we add this read of Y, we see that this can read both 0 and 1 by checking the graph. We continue with one option, say 0, and then we push the other option to some map that we're going to use later when backtracking. This map here, this entry says that the read of Y can also read from the right of 1 there. In the next step, we'll add this right of X. This is execution number 1 from above. And when we add this read of X, this right of X here, sorry, we notice that if this were added before the read, this read could have read from it. So we need to account for that. And we add another entry in our map that we're going to use when backtracking that says that the read of X can also read from this right of X. And I'm going to explain why I have these square brackets there in a second. This concludes the first exploration. And now we start backtracking. We backtrack in a reverse addition order. So we'll backtrack to this read of y. And this is one of the races that we can reverse in an optimal manner. Let me show you how. We will restrict the graph to contain these events here that are the events that were added before the read. We change the reads rf, and then we're done. This is called a forward revisit. It's called a forward revisit because the read was added after the write from which it should read from. And forward revisits we can deal with very effectively. We can even forget about them as soon as we are done. And to deal with them, we just restrict the graph to its previous state. Now, continuing from here, we'll add the write of x again. This is execution number 2. And now we notice the same thing again, that if this write were present when this read was added in the graph, then this read could get read from it. But we've already accounted for that. This is already in our map. And I'm highlighting this red because this is actually a bit of the problematic races that we cannot reverse. And we actually even have to remember that this has happened for as long as the read remains in the graph. Now, let me show you why this is problematic. These are the events that were added before the read here. So I cannot simply change the reads RF to read from there because this doesn't belong in the graph that I restrict to. And actually, the reason why I have these brackets here is because I have to save the prefix of the write that's doing the revisit. This is this pink part here. And for these kind of revisits, when the write is after the read, I have to save the prefix, and then I can change the RF and restrict the graph. This is called a backward revisit. Again, we call this a backward revisit because in these cases, the write is added after the read from which it should read from. And backward revisits are a bit problematic because, again, as long as reads like this one here remain in the graph, then we cannot forget all the sequences, all these prefixes that have backward revisited this read here. Now, the rest of this exploration is straightforward. We'll just add the read of y again. Now, this read of y is encounter another forward revisit, and we mark it in the graph. This is execution number 3. And then we change its RF and explore execution number 4. But as I said, the problem here, the issue with this algorithm, even though it's optimal, is that we have to remember these backward revisits, right? And this is an issue because these sets here for these reads, we cannot get rid of them and they can grow exponentially. So how does Trust solve this? Well, Trust solves this by only allowing backward revisits to happen in specific graphs that we call maximal extension. And this is actually Trust's key idea. So let me show you what I mean by that. Here's an observation, and the observation says that only deleted events differ when the same backward revisit occurs. So this is the 2 previous graphs where the write of x could revisit this read of x. In both cases, if the revisit were to happen, this is the graph that I would get. The pink part is the prefix of the write that I would have to save, and then the olive part is the events were added before the read. Now, what's different in these 2 graphs is the only event that's going to be deleted is this read of y. In this first exploration, it's reading 0, and this one, it's reading 1. And now here is Trust's key idea. This is Trust cornerstone. Trust says that a backward revisit can only happen when the events that are going to be deleted are added in a maximal manner. And when are events added in a maximal manner? Well, we have a precise definition in the paper, but roughly this means that reads read from the latest same location write that was added before them. So in this case, when I added this read here, this read could either read 0 or 1. The event that was added latest was this write of 1. So the revisit is only going to happen in this graph here on the right and not in this graph on the left. And more abstractly, what's happening is that we may have multiple explorations where a write W can revisit a read R, leading to this olive part. And what's going to be different in all these explorations are the deleted events, which are the ones that I have in blue here. And Trust says that you're going to do this backward revisit in only one of these explorations, in the one where the deleted events are added in a maximal manner. And maximality guarantees uniqueness because we pick only one of all possible paths, but also existence, because it basically says that the operational semantics will not get stuck. And now the good news is that if we do that, we can actually forget about backward revisits that we've already explored. As soon as we encounter a backward revisit and then we execute it, we can forget about it because we know that it's not going to occur in any other exploration. Now, does this give me polynomial memory consumption? Well, on its own, it doesn't. But actually, the last thing that trust does to get polynomial memory consumption is easy, and it's basically to revisit in an eager manner. And this means that as soon as we encounter a backward revisit, we just go ahead and explore it recursively, and this will yield polynomial memory consumption. And let me show you why. So here's a property, and I'm going to prove this property very quickly. The property says that the prefix of a write W that backward revisited a read R will never be deleted. So I have a graph G, I add some write W that can revisit a read R, and if it does, it will get this, I'll get this olive part. And now this property says that if I initiate this recursive sub-exploration here from this graph G prime, W and all its causal predecessors are not going to be deleted in this sub-exploration there. And let me show you why. Well, how could this be deleted? Well, the only way in which I can have events be deleted is if some backward revisit occurs, right? But I'm going to show you that for all backward revisits that may happen, W is going to remain in the graph and also its predecessors. So first of all, the backward revisit cannot be like this, because if it's like this and W prime is causally after W, then the prefix of W prime, which includes W and its prefix, is going to be preserved. So W prime could be somewhere there. Now, what kind of reads can this revisit? Well, let's assume that it tries to revisit a read R prime that's added after R. In this case, the graph that I'm going to get is somewhat like this, because R prime was added in G prime after the revisit had happened. So both R and W were added before R prime, and I always keep the events that are added before a read that's being revisited. So in this case, the W and its prefix are being preserved. And the final case is W prime trying to revisit some read R prime that was added before R. In this case, the graph that I'm going to get is going to be somewhat like this. We know for sure that W prime is not causally after W. And we also know that R prime was added before R, and by extension before W prime, before W, sorry. So both R and W are going to be in the deleted events. And now this could remove W and its prefix, but now this backward revisit is forbidden. And it's forbidden because there is at least one event in these deleted events, and this event is R, that's not reading maximally. R is reading from a write that was added after it, this is W, and not from the latest same location write that was added before it, in which case it would have been maximum. So trust basically says, just do all backward revisits early. As soon as you encounter one, just explore that recursively. And then maximal extensions bound the number of backward revisits that you can do subsequently. You can do at most n backward revisits at a given exploration. So this gives you a total space complexity of n squared. Now, in the paper, we have a smart way that can bring this down to linear, but this is a bit more technical, so I'm not going to go over it right now. And instead, I'm going to conclude with some takeaways. By using execution graphs, Trust is able to model weak memory models and have elegant race traversal for approximately half of the races, that is, for all forward revisits. By using maximal extensions, we don't have to remember backward revisits that have already happened. Basically, as soon as we explore one backward revisit, we can forget about it because we know that it's not going to occur in any other sub-exploration. And finally, by revisiting eagerly, that is, by exploring a backward revisit as soon as it appears, and then thanks to maximal extensions, we get polynomial memory consumption. Trust is available on GitHub as part of GenMC, and I'll be very, very happy to take your questions and feedback.